Hey students, 914 is Stoke's theorem. What is Stoke's theorem? We did talk about Green's theorem. Green's theorem, we used it to find the work done on an object who is moving on what? That is moving on what? On a closed curve, but where? In two-dimensional space. Stoke's theorem is talking about how can I find the work done on an object that is moved on what? On a curve, closed curve, but in where? In three-dimensional space, period. This is exactly 914, guys. This is what we have in 914. So it's a generalization of a Green's theorem. Green's theorem, here it is. Remember, this is Green's theorem. This is how we find the work done on object if the object is moving in two-dimensional space. Why two-dimensional? Because this is a two-dimensional space. It's moving on the ground, isn't it? Now, in Stoke's theorem, we need to find the work done on an object that is moving on three-dimensional space. To do that, I must give you the force function, the velocity function, vector field. We take the curl of F. Remember the curl of F, dot product of this, ds. And this is what is the formula for finding the work done on an object that is moving on three-dimensional space in a closed curve. If you recall, if there was no curl here, F, we don't have this one, curl F. What's F dot N with this one? Do you remember this one? This one in the previous section is telling me how to find the flux. But if I change F, imagine, to curl F, this will give me the work done on an object that is moving on a closed curve in three-dimensional space. This is our work, guys, period. This is the end of it. Here's an example. Verify Stoke's theorem. I'm giving you the force function. The object is moving, and S is the portion of the paraboloid. This is our paraboloid. Let's grab the paraboloid. Here it is. Okay. Now, the object is moving. So this is a paraboloid. If you remember, you go to Z equal to 16. And then, you know, when Z is equal to 0, I have a circle of radius 4 in both X and Y. So here we have 4 on the left. We have -4. And here, same thing, we have 4. And in the back, we have -4. So mainly the paraboloid is like this. And on the x-axis, it's just like that. So what's going to happen? The paraboloid is going to continue all the way down. But there will be Z greater than equal to 0. By the way, what's Z equal to 0? This is the XY plane. So the XY plane, here is the Y, and here is the XY. It's going to come. And when I say Z equal to 0, it's this plane. So the plane is going to cut the paraboloid. And what do we have? We have this circle. So the parabola is going to continue down, but Z equals 0 is going to come. So it's talking about Z equals 0 and everything above. So where's my region? My solid is exactly the dome that you see over here. Alrighty, so now what do we need to find? There is an object that is moving on this one on a closed curve. Probably it goes like that, maybe. Goes like this. Maybe he's walking here. Then he's going to go like that. And then he will go up and where it starts. So it goes like that. Or the object can go like this. Goes down, goes down. Okay, and then continues like this, continues like that, continues like this, then up again, then up again, and up again, and up again. So there is a direction that this object is moving on that surface. We need to find Stoke's theorem. What's the Stoke's theorem for finding? We need to find the work done. What's the work done equal to? It's the double integration of curl F dot N, then square root 1 plus Fx square plus Fy square dA over R. Let's take it step by step. I'm going to start with curl F because I know what F is. All right, so let's take the first one, which is actually curl F. How do you find curl F? Remember, we say I, J, and K. Then we put d over dx, d over dy, and d over dz. And then we put here the p, which is 2z, then minus 3x, and this is 4y. And how do you find the determinant? We take the first two columns out. And then j, d over dy, and minus 3x. Now what do? We go this way. So it's going to be the derivative of 4y with respect to y, which is 4. So this is equal to 4i plus, let's go to j. The derivative of 2z with respect to z is 2. And here there is j, here is j. Plus the derivative of this with respect to x is negative 3. So this is minus 3k, because there is a k here. Then minus, open bracket. We go backwards. What's the derivative of 2z with respect to y? It's a 0. 0 what? 0k. Plus this times that times that. The derivative of this with respect to z is equal to 0. So this is 0, but I. How about the last one? The derivative of this one with respect to x, 4y with respect to x is a 0, j. So this is all 0. So I'm left with 4i plus 2j minus 3k. This is the curl of f. Now we need to find n, guys. To find n is the gradient of g over the magnitude of the gradient of g, assuming everything is oriented outward. All right, where is g? You get it from here. Okay, now we have z is equal to 16 minus x squared minus y squared. By the way, this is f of xy. I'm gonna move everything to the left. So z minus 16 plus x squared plus y squared. If I move everything, what do we get? We get 0. So who's this now? Look at this. This is a function of x, y, and z. This is our g. So what's the gradient of g? It's the partial derivative of this with respect to x, which is 2x I, plus the partial derivative with respect to y. Everything is 0 except here, 2yj, plus the partial derivative with respect to z is 1k. The magnitude of the gradient of g is equal to square root of the square of the first, which is 4x squared plus 4y squared plus 1. So that means from all of this, that n is 2xi plus 2yj plus k divided by square root of 4x squared plus 4y squared plus 1. That's n. We got n, guys. Now we have n, and we have the curl of f. Now what do? We do dot product. So now this implies that if I take the curl f, multiply it by n, what do? We multiply the 4 by the 2x, we get 8x. Then this 2 times 2y is 4y. Then minus a 3k times k is minus 3 divided by square root of 4x squared plus 4y squared plus 1. This is curl.f, guys. Now what do we need? We need actually this part now. So now let's take the color, different color here, and let's use the blue. Okay, so let's do it here. We know that f of x, y is that part. Where is it? Remember, this is f of x, y. It's z, huh? It's the z, which is equal to 16 minus x squared minus y squared. This is our surface, the dome that you see there. The partial derivative of this with respect to x is minus 2x. The partial derivative with respect to y is minus 2y. The square root of 1 plus fx squared plus fy squared, which is this part, guys, is going to be square root of 1 plus the square of this, which is 4x squared, and the square of that, which is 4y squared. So what happened when I multiply curl f dot n, all of this multiply by 1 plus fx squared plus fy squared. Remember what's going to happen here. The answer is this will cancel that, and I have 8x plus 4y minus 3. So I'm going to go to the next page and say that the work done is equal to the double integration 8x plus 4y minus 3 dA over r. Now let's go to the graph, guys. Where is r? This is r. What is this? This is a circle of radius 2, isn't it? It's a circle of radius 2. So I'm going to take it here. Okay, so I'm going to change everything to polar. So this is double integration of 8 times. Remember, this is we know that x is equal r cosine theta, and r is here too. So x is equal to cosine theta. So what is this going to be? 2 cosine theta plus 4 times, we know that y is 2 sine theta, it's r sine theta, minus 3, all of this, d, then r, dr, d theta. Now for r, it's from 0 to 2, as you know. And to do the whole circle, it's from 0 to 2 pi. And this is equal to the integration from 0 to pi of 16 cosine theta plus 8 sine theta minus 3. This is r dr d theta. We start the integration from the inside. This is equal to the integration from 0 to 2 pi. I only integrate r, which is r squared over 2. So this is 16 cosine theta plus 8 sine theta minus 3. This is all r squared over 2. This is the integration of r. This from 0 to, what are the, I missed the integration here. There's an integration here from 0 to 2. So this is from 0 to 2 d theta. Put the 2, guys, you get 4 over 2, which is 2. So this is equal to the integration from 0 to 2 pi. So by the way, all of this is 2, right? Put the 2 here. 4 over 2 is 2, and then 0, so it's 2. Multiply it by 16, so you get 32 cosine theta plus 16 sine theta minus 6 d theta. And this is equal to, the integration of cosine theta is sine theta, so this is 32 sine theta minus 16 cosine theta, because the integration of sine is minus cosine, minus 6 theta, and this is from 0 to 2 pi. So we start with 2 pi, sine 2 pi, minus 16 cosine 2 pi, minus 6 times 2 pi. Minus now, we put the 0, 32 sine 0, minus 16 cosine 0, minus 6 times 0. Sine 2 pi is 0. Sine 0 is 0. This is 0. So what's left? Cosine 2 pi, by the way, is 1. So you have negative 16. This is also 1. So, yeah. And this one, sorry. This is minus 12 pi. So we're done with this and we're done with this. Minus 16 again. And this is equal to minus 32 minus 12 pi. This is the volume. This is actually the work done. Okay. So now we are done with the work done using that example. Now let's do that one, Stoke's theorem again, where C is this triangle, guys. So we have okay, just a second. Here is the graph. The 1, 0, 0 on the x-axis, here it is. Let's see, here's 1. On the y-axis, here's the 1. On the z-axis, here's the 1. Connect those points. And connect these 2 points. Connect this 1 point. Right, so we have a pyramid. Now in this one, what would be z here? If you have all of this is 1, can we say this is x plus y, and let's say here, let me remove this one. Probably the best presentation of that one is x plus y plus z equal to 0. How about that? Right? This is the surface because it's 1, 0, 0, 0, 1, 0, and 0, 0, 1. If you take x and y 0, you get z1, right? So I don't mean 0, I mean 1. If you take x and y 0, you get z1, here it is. If you take x and z 0, you get y1, here it is. And if you take y and z equal to 0, then x is equal to 1, here it is. So the best presentation is x plus y plus z is equal to 1. So this implies that z is equal to 1 minus x minus y. From this one, this is actually f of xy. So what I'm going to find here, I will find the partial derivative with respect to x, which is -1. The partial derivative with respect to y is also -1. So this will give me that the square root of 1 plus fx squared plus fy squared is equal to the square root of 1 plus 1 plus 1, which is the square root of 3, right? This is the one of the things in the function, in the work done. What's next? Probably we can look at curl f. What do we put? We put I, j, and k, d over dx, d over dy, d over dz. The p here is 2z plus x, and the next one is y minus z, and the last one is x plus 1, x plus y. What do? We take the first column, and 2z plus x, take the second column, and y minus z. We go in this direction, guys. So what is this equal to? The derivative of this one with respect to y is 1i, because this is I. Let's look at j. What's the derivative of this with respect to z? This is 2 and this is 0. So plus 2j plus, what's the derivative of this with respect to x? I think it's a 0. So we get 0k minus, let's go this way. What's the derivative of this with respect to y? It's 0. 0 what? 0k minus. What's the derivative of this with respect to z? It's -1, and there is a minus, becomes plus 1i. The derivative of this with respect to x is 1, so minus 1, and this is j. So what do we have now? I, and I is 2i. 2j minus 1j is actually 1j. 0k, 0k is gone. So this is what's left in curl f. Now we need to find n. So what is g? Now you have in this, we have x plus y plus z equal to 1. Move everything to one side. So x plus y plus z minus 1 is equal to 0. This implies that g of x, y, and z is what? It's x plus y plus z minus 1. The gradient of g, it's the partial derivative of g with respect to x, which is 1i, plus the derivative partial with respect to y is 1j, plus the partial with respect to z, which is 1k. Gradient of g magnitude is going to be the square root of 3. It's 1 square plus 1 square plus 1 square. So this implies that n is I plus j plus k over square root of 3. What do I need? I need curl f dot n. Where's curl f, by the way? This one is curl f, which is 2i plus j plus 0k multiplied by this number, I plus j plus k over square root of 3. 2 times 1 is 2. 1j plus 1j is 1. 0k divided by square root of 3. And this is a 3 over square root of 3. Now, curl f dot n times the square root of 1 plus fx square plus fy square. All of this is a 3 over root 3 times, we know that this is root 3. So the final answer is a 3. So now, what do we say here? We said that the work done, Stokes means the work done, is equal to the double integration. Everything is nothing but 3. dA over R. You can take the 3 out. I'm left with the area of the region. Where's my region? This is my region. It's the base of that thing. What is this, by the way? This is a triangle. This is a triangle. This is a triangle. What's the area of that? It's half times the base times the height, which is half. So by the way, this is equal to the 3 times the area of the triangle. Why triangle? Because the region is a triangle. There is nothing inside. We said when there is nothing but 1 here. So the area of the base, and this is a 3 times half, and the answer is a 3/2. This is exactly Stokes' theorem. This is the work done. Let's verify this. Stokes' theorem again. He wants to find the work done on an object moving. You see, it's in the space, moving in the 3 dimensions, moving on that thing. All right, so he's telling me that z is equal 1 over y. So z is equal 1 minus y. And who's this? This is f of x and y. Okay, so let's find the partial derivative with respect to x. There's no x here, so it's a 0. Let's find the partial derivative with respect to y. It's -1. So this implies that the square root of 1 plus fx square plus fy square is the square root of 1 plus 0 is 0, and then you square the negative one, you get 1, and this is root 2. Now let's talk about curl F. This is the lengthy one, I, well, d over dx, and then we have z squared y cosine xy, and then j with d over dy of z squared x 1 plus cosine xy, and then k 2z sine xy, and this is d over dz. What do? We take the first column out, d over dx, and then z square y cosine xy, j d over dy, z square x 1 plus cosine xy. All right, let's go this way, guys. What's the derivative of this one with respect to y? Y is here. So this is equal to, this is a constant, we don't touch it, 2z. What's the derivative of sine? It's cosine xy times the derivative of xy with respect to y, which is what? X, so we put it at the beginning. And we say I plus, now let's go to the j. What's the derivative of this with respect to z? The derivative of z squared is 2z, so this is 2zy cosine xy, and this is now what? J. Plus, let's go this way. What's the derivative of this with respect to x? Wow, it's the first times derivative of this inside with respect to x. The derivative of cosine is minus cosine xy times the derivative of xy with respect to x, which is y. So this is the derivative of the inside, plus 1 plus cosine xy times the derivative of the first one with respect to x, which is z squared. Now minus. Because this one, don't forget, this is what? The last one is k. All right, now let's go to the backwards. What's the derivative of this with respect to y? Same thing, it's the first times derivative of the second, which is minus sine xy times the derivative of xy with respect to y, which is x. This is k. Sorry, then plus the second, which is cosine times the derivative of the first with respect to y, which is z square cosine xy, all of this j. Sorry, all of this is k. Because we're talking about k. Now let's talk about I. What's the derivative of this with respect to z? You have z square here, so it's going to be minus 2z x 1 plus cosine xy, all of this actually I, minus the last one is this one. What's the derivative of this with respect to x? We only differentiate the sign, so this is 2x cosine xy. The derivative of this with respect to x is y, here is y, and this is j. Okay, so let me just fix that one and make it a clean k. That's okay. Now, guys, let's look at the I. Here's I. Where's the other I? So this is all. Okay. The other I is here. So we have 2z2 zx cosine xy minus 2zx minus 2zx cosine xy. This is all I. Go to j plus 2zy cosine xy. Where's the other j? The other j is here. Minus 2xy cosine xy. And this is j. Then the last one is k. What do we have for the k? We have plus z square times x times y cosine xy with minus, because there's a minus here. And this one plus z square plus z square cosine xy. And then the other k is here. So minus with minus is plus z square xy sine xy minus z square cosine xy, and this is actually all k. This one cancels this one, so we are left with 2zxi. We check the correct work. And 2 minus 2x minus 2zxi. It's a negative for the I. So yes, there is a minus here. My apology. Here is the minus. All right. Now for this one, I noticed that there will be no j. So for that part, this one actually, when it comes to j, here the derivative of this one with respect to z is 2zy. Where am I for the z? We're talking about j. J here it is 2zy cosine xy. And when you go back here, this is 2zy cosine xy, 2zy cosine xy. Where am I here? 2zy, not xy, cosine xy. So this one cancels that, 0. Now here, z square x with this one cancels that one. Okay. And let me check the z square k. It says z square k, and this one actually cancels that one, and we are left with z square k. That's the final thing for the curl of f. Now what do we do? Because this is cosine, not sine. So what do we do now? We have the curl of f. Next is to find n. So what do we have here, guys, for z? We have z is equal 1 minus y. Move everything to the left. So z minus 1 plus y is equal to 0. Who's that? So that means g of x, y, and z is equal to z minus 1 plus y. Gradient of g is the partial derivative of this with respect to x, which is 0i, plus the partial derivative with respect to y, which is 1j, plus the partial derivative of g with respect to z, which is 1k. The gradient of g magnitude is the square root of this 0 plus 1 plus 1. It's a square root of 2. And it has, as you know, always I say it's match. They have to match. Huh? So n is j plus k divided by square root of 2. Now what do we do now? We take curl f dot n. What's curl f dot n? Here is curl f. So it's minus 2zx times 0. Because here in n there is no, this is 0i. Huh? Then for the j, there is no j here. So plus 0j on the first one and with 1 in the second one. Plus z square in the first one times 1, so z square. So this is 0, this is 0, divided by square root of 2. So it's z square over root 2. Altogether, curl f dot n times the square root of 1 plus fx square plus fy square is nothing but z square, because this is going to go with that one. So the final thing is z square. So let's go now to the work done. It's the double integration of z square dA over r. Now, what is r? And by the way, z square is, what's z square in the question? It's 1 minus y square. So this is equal to the double integration of 1 minus y square. Now, let's look at the base. Where is the base, by the way? This is the region. Here it is. By the way, this is 1, right? Because when z is 0, y is 1. So this is 1. So on the y-axis, 1. On the z-axis, on the x-axis, it's 2. So the region is like this. 2 here, 1 there. This is our region R. So I'm going to say here, dx dy. And so I'm going to take the region of type 2. So on the x-axis, on this one, I'm going to start with what? With y equals 0. And this is y equal to 1. For the y, from 0 to 1. Now the length, we're starting from where? From x equal to 0 to x equal to 2. So it's from 0 to 2. Where do we integrate from? We integrate from the inside. So this is equal to the integration from 0 to 1. Now, 1 minus y square, we don't have to touch it. 1 minus y, so all square. It's a constant, right? 1 minus y all square is a constant. Because we integrate with respect to x. What's the integration of dx? It's x. From 0 to 2, and then we say dy. Now, what do we do? This is the integration from 0 to 1. Put x2, you get 2, so this is 2, 1 minus y square dy. And this is equal to the integration from 0 to 1. If I expand this one, it's the square of the first, which is 1, times 2 is 2. Then the first times the second times 2, minus 2y times 2 is minus 4y. Then the square of the last, which is y squared times 2, is 2y squared dy. The integration of 2 is 2y, minus the integration of y is y squared over 2, and there's 4, so 2y squared. The integration of this one is 2y cubed over 3, and this is from 0 to 1. What do we put? Put the 1 first, you get 2 minus 2 plus 2/3. If you put the 0, you're going to get zeros, so this cancels that, and the answer is 2/3. This is the work done. Let's look at our last example. Again, Stoke's theorem. Let's look at the gradient. So let's look at curl f. Let me get rid of curl f. I, j, and k. D over dx, d over dy, d over dz, and then you have x square y. The second one is x plus y square. The last one is xy square z. We take the first column out, and x square y. We take the second column, d over dy, and x plus y squared. Alrighty, now let's go this way. What's the derivative of this with respect to y? This is equal to 2y times x. So this is 2xyz. And with respect to what? With respect to I. Plus, let's go this way. What's the derivative of this? This is, of course, z. What's the derivative of this with respect to z? It's a 0, j. Then you go to this one. What's the derivative of this with respect to x? The derivative of x is 1 and this is 0, so it's 1k. Minus. Now where do we go? We go this way backwards. The derivative of this with respect to y is x squared. X squared what? X squared k. Was now this k. Now let's look at the I. What's the derivative of this with respect to z? Nothing. It's a 0. So minus 0 I. Finally, minus this times this times this. The derivative of this with respect to x. The derivative of x is 1. I'm left with y squared z. And this is j. Let's join them, guys. I here and I here. So it's 2xyzi. 0j minus this. So it's going to be minus y squared zj. Okay. 1k minus x squared. So plus 1 minus x squared k. This is, guys, the curl of f. Now, what do we do with curl of f? We have to multiply it by n. So what's n? We know here, he's telling me that z equal 9 minus y squared. So z minus 9 plus y squared is equal to 0. So g of x, y, z is nothing but z minus 9 plus y squared. The gradient of g, first we differentiate with respect to x. There is no x here. That's a 0i. Then we differentiate with respect to y, which is 2yj. And then we differentiate with respect to z, which is 1k. This implies that the gradient of g magnitude is square root of the square of the 0. So you have 4y squared plus 1. Which implies now n is 0i plus 2yj plus k divided by square root of 4y squared plus 1. That's n. Now we take curl f dot n. What do we get from this one? Curl f is this multiplied by 0, it's gone. So it's a 0i. Then this one with this one is minus 2y cube z. My apology, there is no I. Huh? It's a dot product. There is no I. Okay, it's a dot product between curl f and n. And finally, for the k, you have 1 minus x squared times 1 is plus 1 minus x squared. This is divided by square root of 4y squared plus 1. Now, if we take it all, curl f dot n times, oops, we don't have that one yet. I will leave it to you, by the way. You know that, where is z? This is z. So f of xy is 9 minus y squared. What's the partial derivative with respect to x? 0. What's the partial derivative with respect to y? It's minus 2y. So that means the square root of 1 minus plus fx squared plus fy squared is equal to the 1 plus, we know this is 0. Square that one, you get 4y squared. As I always say, this one must match what? The gradient. So altogether now, curl f dot n times the square root of 1 plus fx squared plus fy squared. What's going to happen? Curl f dot n is here, guys. This is curl f dot n. If I multiply it by this, that will cancel this. So I'm left with what? Minus 2y cubed z plus 1 minus x squared. This is curl f dot n. So now what's the work done? It's everything we have here, which is minus 2y cubed z. By the way, what's z? Z in the question is 9 minus y squared. So 9 minus y squared plus 1 minus x squared, all of this dA over r, which can be simplified. If I multiply here, you get minus 18y cubed plus 2y to the 5 plus 1 minus x squared dA over r. Now, where is r, by the way? This is our r. Let me take it here and graph it. It's this triangle on the y, it's 3, 1, 2, and 3. And then what do you have? You have y equal to x. This one is y equal to x. And it goes like this, right? This one is y equal to x. I'm going to consider that this is a region of type 1. So I will take now a vertical sector. This is going to move from where? Starting from x equals 0 to x equal what? What is this? If y here is a 3, guys, so what's this? So x here would be 3 over 2. This is the intersection of this one. You have y equal to x, and also here you have y equal to 3, right? This is the intersection between y equal to x and y equal 3. So that means 2x is equal to 3. So x is 3 over 2. So this is really 3 over 2. So this is equal now, double integration of minus 18y cubed plus 2y5 minus 1 plus 1 minus x squared dy dx. X, as I said, is from 0 to 3 over 2. How about for the y? Who's at the bottom? When you take these sectors, who's at the bottom? Y equal to x. To the top, which is here, y equal to 3. All right? So now you start the integration from inside. And you integrate with respect to y. So this is 0 to 3 over 2. What's the integration of this one with respect to y? It's minus 18y to the 4 over 4 plus 2y6 over 6 plus y minus x squared y. Integration of this one is x squared y. And this is from 2x to 3. And then dx. So what do we do now? We said this is the integration from 0 to 3 over 2. Now this one is 2 and this one is 9. So it's minus 9 over 2. We will put 3 to the 4 plus this one with this one is a 3. Put the 3. So it's a 3 to the 6 over 3 plus put 3 minus x squared times the 3. So 3x squared. Minus now. What do we plug? We plug the x here. So it's going to be minus 9 over 2, 2x to the power 4, plus put 2x here. You get 2x to the power 6 divided by 3, minus x squared times 2x. And all of that is dx. I leave this one for you guys to finish. And I think you will get at the end minus 125.2 is equal minus 125.2. This is the final answer. It's just a matter of simplification and integration, guys. And this is how you apply the curl F in Stoke's theorem to find the work done on an object. Hope you enjoyed, guys. So we left with 2 more sections, and they are very easy. So somehow lengthy but easy. We're going to talk about the triple integral now and how we apply it to something called the divergence theorem. The major thing in this chapter is Green's theorem, Stoke's theorem, and flux. And then I'm going to take you to the divergence theorem. Divergence theorem is related somehow to the triple integration. So we have to discuss triple integrations to see how can I apply the triple integrations in finding the flux. Okay, you guys have a good day.